The topic we will discuss today is nucleophilic substitution unimolecular reaction, that is SN1 reaction. Now, SN1 reaction is basically a carbocation based reaction, that is, the reaction goes through the carbocation intermediate formation. Now, first of all, we will write down the full name of SN1 reaction, that is substitution nucleophilic unimolecular. Here the term unimolecular represents that the rate of the reaction is dependent upon only the concentration of reactant, not on the concentration of nucleophile. Now we will try to elaborate the overall SN1 reaction with a proper mechanism. Let us consider a substrate with halide CX. One group is R, that is alkyl group. Another is one alkyl group. Let's suppose it is R prime, and the third one is also an alkyl group. Suppose it is R double prime. At the first step of this reaction, the leaving group or the halogen departs from the molecule and a carbocation is generated like this. Now, the overall reaction rate depends upon the stability of this carbocation. Now, the X group may be any halogen group, any halogen atom, except fluorine, or any good leaving group. Let's suppose it may be OH, OMe, etc. Now, here we can see the carbon in the substrate or the reactant is sp3 hybridized, but when the reaction starts, it forms the carbocation where the central carbon atom becomes sp2 hybridized, hence the structure changes from tetrahedral to planar shape. This is a very basic concept of this reaction. Now, if we draw the structure of carbocation in terms of p orbital, then we can see that the positive center of carbon is nothing but a vacant p orbital. This is a vacant p orbital which has two lobes. Now, if a nucleophile approaches to the carbocation to attack it, then it can attack from the right side. Also, the nucleophile can attack from the left side, as both sides are available here. Now, if the nucleophile attacks from the left side, then we can see that this part R, C, R prime and R double prime goes towards the right side and the nucleophile adds from the left side, as well as if nucleophile adds from the left side, then this part will go to the left side. Now, two molecules will be formed here. Now, let's see the two molecules. Nucleophile carbon R, this is R prime, this is R double prime, plus another molecule formed is R, this is R prime and it is R double prime and nucleophile adds to the right side. Now, if we minutely see the two structures, then we can conclude that the two structures are mirror image to each other, but they are non-superimposable. They are mirror image to each other, but non-superimposable. It denotes that it is nothing but a 1:1 racemic mixture. Racemic mixture is nothing but a 50-50 ratio or equimolar ratio of two enantiomers. These two isomers are also called enantiomers, as they have mirror image relationships with non-superimposable character. Now, the rate of this reaction hugely depends upon, as I told earlier, that on the carbocation stability. Now, let us see on what factors the carbocations will depend. According to the carbocation stability, the factors which affect the stability of a carbocation mostly are: number one is resonance effect, number two is hyperconjugation effect, and number three is plus I effect, that is positive inductive effect. The most effective is among these is resonance effect. This is the most effective part here, and the second most effective part is hyperconjugation. The third most is plus I effect. Now let us consider a chemical reaction, or specifically an SN1 reaction. Let two substrates are given here, CH3, here C2H5, and here pH, or let's suppose it is not pH, it is CH3 again, it is Br. This is substrate number A, and we have given another substrate where carbon is surrounded by one CH3 and two hydrogens, and the leaving group is same, that is Br. Now we have to, let's suppose it is B. Now we have to compare between these A and B, that which one would likely participate in SN1 reaction mostly. Now we can see that the first compound or the first substrate is filled with very much hyperconjugative effects and plus I effects also, but the second one has only one hyperconjugative effect of CH3 group and one plus I affecting group, that is CH3. Now let's see how much hyperconjugative effect is affecting here and affecting here also. The carbocation formed from A will be like this: CH3, C2H5, CH3 plus. Now if we draw the structure clearly, then we can see C, H, H, H. Now let's suppose it is drawn in Fischer projection, C, H, H, then CH3, again carbon with 3 hydrogens. This is positive charge. We know these carbons are alpha carbons, so these hydrogens can take part in hyperconjugations. These hydrogens also. Now the hyperconjugative hydrogens are 3 plus 3 plus 2, that is 8. So here 8 hyper conjugable hydrogens present. Now if we see the carbocations formed from B, carbon with one CH3 only here. Now these two are hydrogens and this is carbon positive. So here are three hyperconjugable hydrogens. Three hyperconjugable hydrogens only. Now, according to the hyperconjugation effect, the more hyperconjugable hydrogens present will be the more effective structure or the more stable structure. So, in this context or concept, the carbocation formed from the substrate A will be more stable than the carbocation from B. Hence, we can say that A will be more and more effective in giving SN1 reaction than B. So SN1 reactivity order will be A greater than B. Thank you.